Thank you, Stefan. All right, I'm very excited to be here, so let's dive straight in. So, short raise of hands. Who of you has experienced or maybe even caused this screen? Just raise your hands. All right, perfect. You're in the right place. We're gonna find out how we maybe have this screen less often by using Rust. So a little bit about me. I'm currently studying computer science bachelor at GQ, that's in the west of Austria, and I'm hopefully done by the end of this year. And as Stefan already said, I've been using Rust since 2020, 4 years ago. And before that, I've been dabbling with C++ and wrote a bunch of projects with it. I'll come to that in a second. And generally, I'm really interested in low-level programming, kernel drivers, but also many other things, hypervisors, EFI drivers, and so on. I also like game security. It's a really interesting topic, software security in general, and also reverse engineering. And why am I speaking about kernel drivers with Rust? As it happened to be, 4 years ago, I was currently writing my A-levels exam, and I figured, isn't there better use of my time than like studying? So I rewrote a bunch of old projects of mine that I wrote in C++. One of them happened to be a kernel driver. I rewrote those in Rust, and I learned a bunch of things there. And it wasn't really that easy. So I also decided to write a blog post about it. Then eventually also gave a talk about it. And then as time evolved, I released a bunch of projects, crates, just to make kernel driver development much easier in general. And let's take a look, how did we even get here? I certainly wasn't the first person to write a kernel driver in Rust. As it turned out, already 8 years ago, Probric released their proof of concept, but it was quite messy, and I personally wasn't able to get it to build because they patched libcore due to some float stuff, and they also hard-coded the static libraries. In 2019, Trendtext released another proof of concept, which was already much nicer because it used Cargo X build, but it still wasn't quite ideal. And they also forked the, at that time, very popular Win API bindings and added kernel bindings. I and many people after me used these bindings. And then in 2020, as already mentioned, I released a code, blog post, and talk how to write a kernel driver with Rust. You didn't need to use Cargo X build. You could just use your normal Rust installation, set some feature flags, some linker flags, and that's it. And then not much happened. People were also writing blog posts, building their own kernel drivers, but we never got official bindings until Microsoft in 2023 released official bindings for the WDK. And here we are. So let's take a few steps back just to get all on the same level. What exactly is a kernel driver? And a kernel essentially is an interface for applications to interact with hardware and the CPU and memory. And you can think of a kernel driver like a plugin for the kernel, because kernel developers at Microsoft can't do all the work on their own. And maybe you've stumbled upon them. You can generally recognize kernel drivers with the .sys extension. And kernel drivers really have access to everything. That includes hardware, memory, the CPU. So it's very dangerous and a critical part. And they're really everywhere. Every machine uses kernel drivers, starting from your hardware manufacturer, like the GPU drivers from NVIDIA or AMD, but also anti-cheats and antivirus companies are using them because they want to ensure that the system is protected. And because of that, also cheaters and hackers are also going to the kernel to evade those security measures. Yeah. And you really have to be careful because you have so much power. That also means if you crash, that means you'll have a blue screen. And common examples of that include having unhandled exceptions or corrupting critical data. And the most recent example that probably all of you have heard of is the CrowdStrike incident. And as we saw, this can have drastic impact. So with all of that in mind, let's write the kernel driver in Rust with the official bindings. And there's a few prerequisites. Unfortunately, for all the Linux people here, I hate to disappoint you, but you'll have to install Windows. Currently, there's no easy way to do it on Linux, but maybe we can do that in the future sometime. You also need the Windows driver kit, which includes all the include headers, libraries, and so on. We also need LLVM to automatically generate bindings at build time. And of course, we're going to use Rust. So the first step, all of you know it, we generate a new project called Hello World, and in this case, it's a library. And then we already need to make sure that we're building a dynamic library. On Windows, if you compile this will be a .dll, which is basically kind of the same as a .sys as a driver. And we also need to disable unwinding because it's currently not supported. We also need to make sure that we're using the static CRT because we don't want the driver to link to any user mode libraries. And then we already generate the build script, which is the most important part because it's going to detect your WDK that you installed and also automatically generate bindings for it. And additionally, it also sets some linker flags, which make sure that you're actually compiling a driver which can be loaded later on. And the WDK, the official crate by Microsoft, makes it really easy. It's a single function call, and then you add the metadata to your cargo.toml, and it just works out of the box. Then we can already write our kernel driver. And the first step is we have to opt out of STD, because this is like an embedded project. It's not available. Therefore, we also have to write our own panic handler. Often, there's a very simple panic handler with just a simple infinite loop. And this is also implemented in this crate like this. But I would recommend against using this in a production system, because if your kernel driver panics, you won't have any information. So you'll know something happened, your kernel driver isn't responding, but it won't give you any clue or information about it. And then we can already write the entry point. And in C or C++, this looks like this. We have some includes, then we have a driver entry, which is the main of the kernel, and then we get two parameters, a pointer to a driver object, and also a constant pointer to a registry path. And then in the body, we can do something simple like printing hello world. And the Rust version for this looks pretty similar. We also include all the types that we're using. Then we're defining a function called driver entry. We need to set some linker flag so that the exported name is actually the same. We could do the same by just using nomangle. And then we get the same parameters. And instead of calling debug print directly, which is a C function which uses normal format string, we can use something more ergonomic. In this case, it's the println macro defined in the WDK crate, which is more ergonomic and more Rust-like. And after that, you could already build your kernel driver using cargo build, but you couldn't load it because this driver needs to be signed. So if we use the official makefile that is provided for us, we can then call cargo make, and it automatically generates a certificate. It also automatically signs this driver, which just makes our lives easier. And then we also need a .inx file, which is just some documentation and some description of what the driver is doing. You don't have to write it your own. I recommend going to the official examples, just copying it, adapting it, as we programmers usually do. And then we can already build the driver. In this case, we're using cargo make, and we're building a release profile. And then the driver will be located in our target folder, like you know it. Before running it, we have to enable some flags, because it seems like a very bad idea to let everybody load their own drivers that they built on their own machine using a self-signed certificate, because there's no way to prevent bad people from doing the same. So in this case, we're enabling test signing, which makes sure that we can install our own drivers, which we signed with our own certificate. And then we also enable debug mode. And then you could already load it using the service controller, which is using the command line, maybe not that ergonomic and nice. I recommend using a tool like ORSR driver loader, where you just select the driver path, click on register service, start service. That's it. Your driver is running in the kernel. And then you can hopefully see the output. there's a small caveat. Per default, debug print output is disabled on Windows installations. So you have to go into the registry, set this small value, and after that, you can use debug view and see the outputs. All right. So we defined our first Hello World kernel driver, but there's certainly more we can do. So let's dig deeper and find more neat tips and tricks that are useful. As it is right now, docs.rs doesn't have documentation for the WDK and other crates that Microsoft provides. So once you install your local build system and your driver actually builds, you can use the cargo doc command to open and build the documentation locally. And this will look like the image on the right. Also for debugging, I highly recommend setting up a virtual machine. Because every time your driver panics or maybe even blue screens your machine, you have to restart and set up your development environment and open all the programs again, which is very annoying. Trust me, I've been there, done that, wouldn't recommend it. If you have set up a virtual machine, you can then also use WinDebug, which is a debugger, and you can attach to this virtual machine and then use breakpoints to investigate certain spots. And I highly recommend using this debug break macro instead of the debug break function in the WDK, because the macro makes sure that you're actually going to the right place, and that then you don't see an additional function call. And here it's just a simple breakpoint with some raw assembly. But you can also just use debug view, as we saw before with the Hello World example, and debug using that. Or maybe a better way to debug using debug print is to use the log crate. And here, we can implement different methods. For example, we could use the debug print or the WDK print line we used before, and we can wrap it in with the log trait. Or, in some cases, it also makes sense to use serial logging. Because, for example, in a hypervisor, when you're running the hypervisor, you don't want to call to the NTOS kernel debug print, which does a bunch of I/O inside, which is not ideal. And serial logging is much more minimalistic and really makes sense there. So if you want to use debug print, I already created a crate called kernel log, and you can already use it in your kernel drivers. It's really simple to use. You just specify kernel logger init, then specify the required log level, and initialize it. And then you can use the log crate. So how does it work in the background? And again, it's not that complicated. We have to use the log crate, and we implement the log trait for kernel logger. We're not interested in enabled or flush. We just leave them like they are. And then we create a message, which is a Rust format string, where we pass the level and some additional information. And then we pass it to debug print. And there's two important things here. First of all, in the message, we have to pass the null terminator. If you don't do this, you'll print random garbage and maybe even crash your machine. And you also need to pass the \n, because otherwise you'll print something, but nothing will appear in debug view. And you think something is broken, but actually it's working. It's just, yeah. So add the new line. And serial logging, I highly recommend using the comlogger crate, which already does all the complicated stuff behind the scenes. Set it up with the builder pattern, specify the port, the required log level, that's it, and then you can use the log crate again. Another important concept is custom allocators, because we used the format macro before in the debug print logger, but format allocates. So you need to set a global allocator. But do you want to allocate physical or virtual memory? Should the memory be no execute, read-write execute? Should the memory be page aligned? Should it be cached? Should it be contiguous, so like in one memory area? So there's like a lot of complexity going on behind the scenes. But luckily in our case, we can write our allocator pretty easy. We have to use the unsafe allocator API, and then we can implement this trait called allocator, and we need to define two functions, allocate and deallocate. In allocate, we get a memory layout, which includes the size and some alignment. So there, we can just call a Windows API function, For example, to allocate page-aligned, readable, and executable memory. And in deallocate, we can just free this pointer again. Luckily, in our case, Microsoft already has a crate that does that. Unfortunately, right now, they only implement global alloc, which allows you to set this allocator for virtual memory as a global allocator. And if you've been to the talk yesterday about allocators, you already know this. Use the global allocator macro, and then you can set it. Also have a crate called Kernel alloc, which is similar, but it does more. So it also supports global alloc, but it also supports the allocator API. And there, it supports both virtual memory, either read-write or read-write-execute, depending on your needs. And it also supports physical memory, which is sometimes useful, for example, when you're developing a hypervisor, because certain structures need to be in physical memory. And the usage of the global allocator is the same again. And the allocation API is really powerful because you can use all the types, the collection types from Rust, for example, box or vec, with your custom allocator. So by default, it's using the global allocator. But if you want, for example, here, if you want to allocate 5 in physical memory, you can do this in Rust. This is really powerful. Unfortunately, there's a small problem here. And that is heap allocation currently, as it is in Rust, isn't possible. So in the code example here, if you have an array that's 6 page sizes long, it will first be allocated on a stack and then copied to the heap, so the allocated memory. And this is a problem, because in the kernel stack is only 3 pages long. And with this 6 pages of memory, we instantly overflow the stack. And that's not ideal. So for example, while I was developing a hypervisor for AMD or Intel, I often ran into this issue. And the solution for this is currently you have to use the new zeroed or new zeroed in methods, which first create a zeroed instance, and then you can assume that it's initialized, and then you can set the fields individually. And if you're writing a kernel driver, you also need to interop with other APIs. And generally, I highly recommend just use the official WDK sys or WDK crates, because they have almost anything you need, unless you want to use undocumented functions. And another tricky part is macro functions. So there are some cases where you need to define something on your own. So generally, it's also possible to import all these functions in the kernel manually. And this makes sense if you're just developing a small crate and you don't want to pull all the WDK build and sys crates, because they're quite big and it takes some time and it makes the whole build process more complicated. So if you want to import them manually, you can create an extern block, probably all of you know it, and then we also have to set a linker flag so the linker knows which module it's importing those types from. And then we can define the functions with their types. And this works for both documented and undocumented functions, as long as they're exported. And we can do the same thing for global variables. In this case, KDebugger not present is very useful when you want to only set a breakpoint when there's actually a debugger attached to the system. And here we can define the type and can then use it in our code. But officially, it's not in the crates by Microsoft. And then there's another problem with macro functions, because currently bindgen doesn't know about them, because macros are just text replacements. So here we have a function called keraiseRQL, which gets 2 arguments, but there's no way for bindgen to automatically generate, so we have to manually generate it in Rust. In this example, you might think, that's not that complicated. But what if we have something like this? It gets complicated quite fast. And if you're using this function often, it gets quite annoying if you have to define it on your own and if it isn't in the official crates. And there's also another issue going on here, because overlay is a union. So the Windows kernel tries to optimize also for size. And bindgen has some issues with that. So as you can see at the bottom, there's some bindgen anon, and that comes from unions. All right, so we learned how to write a hello world kernel driver. And we also learned about some tips and tricks here and there. But let's reflect, why are we actually not using C++? And the reasons are quite simple. The C++ standard library uses lots of exceptions internally. And C++ exceptions are not quite the same as the exceptions in the kernel, the structured exception handling. So we can't really use the standard library in C++. And even if it worked, exception handling takes quite a lot of stack space, which we don't really have in the kernel. And also dependency management in C++ is far from ideal, so we're potentially missing out on some really interesting projects. Just because they've been written for user mode, we can't use them in the kernel. And also documentation is a little bit lacking. There's one document by Microsoft from 2004 where they state, we neither endorse nor discourage you from using C++ in the kernel. So maybe that's why nobody is using it. So why should we use Rust in the kernel now? And first of all, the modularization of core, alloc, and std is quite amazing. Because we opted out of std, we can't use it. And core, because we didn't opt out, is always available. And alloc is only available if we define our own global allocator or if we pass our own allocator. And the development experience, all of you know it, is also amazing. With Cargo, Rustup, Crates.io, theoretically we could pull a WASM engine from Crates.io as long as it supports NoSTD, put in the kernel driver, and just run it, and no issues at all. And then also with zero-cost abstractions with all the traits, trop, global alloc, allocator, they're quite amazing. Also, the memory safety features, we heard it in a talk yesterday already, are also really interesting for big companies like Microsoft, because they just remove vulnerability classes that C++ or C have. And this is achieved with ownership and lifetimes. However, currently, there's still lots of uses of unsafes, which makes it possible to still make mistakes even when using Rust. And as we saw in the talk yesterday, Unleashing the Ferris Within, Microsoft is investing lots of time, energy, and money into getting Rust into the kernel and Windows in general. So here in 2023, Microsoft already released a kernel driver that used Rust. However, there are also some limitations. Well, C++ has some issues with exceptions in the kernel. Well, Rust does also. So currently, exception handling isn't supported in Rust because it's quite different with panics and how it handles errors. And the kernel requires exception handling in a lot of parts. For example, when you're reading memory from user mode, or when you're doing paging I/O, if the file isn't accessible anymore, this will raise an exception. And this code in C or C++ is usually wrapped, or is always wrapped in a try except block. And in Rust, we don't really have the concept. And there's one solution. It's not perfect, but it's the micro SCH crate. And how it works is they define the C code, which implements an exception handler, and then ported it and included it in a Rust crate, and then you can call it also within Rust. It's not a perfect solution, so maybe in the future in Rust we'll have something better, but for now, this works. Also, as I mentioned before, bindgen and unions don't really work well together, so we get this giant mess. And then there's also small other things. For example, there were some issues on Windows 10. When you're building a kernel driver, you couldn't load it or you couldn't build it at all. Then there's also some missing APIs from time to time. The usability generally could be improved. For example, there's types that are often used for indexing in an array, and these types are U32. So every time you use them, you have to manually convert them to usize, which is not ideal and could be changed easily. Also, as I mentioned before, the documentation isn't available currently, so you have to build it on your own. And maybe in the future, we also get Linux support, but I'm not putting money on that. So to conclude, we have official bindings and crates from Microsoft, and Rust clearly provides advantages over C++. However, there's still more work needed, but I'm really excited to see what you and Microsoft come up in the future. Thank you.